I'm doing homework. Hello, my name is Gabrielle Taylor. I'm doing homework 3, part B. So, in part A, what we did was we derived the concentration of the distillation column. So, the concentration of, the X and the more volatile component over each stage due to time. So we did this, and then through that we were able to do a McCabe-Thiele graph, and that was showing the stages in the distillation column. So now in part B, what we're going to do is we have a reflux ratio currently of 2. We want to ramp that up to 4, and we want to do this over a time step from 20 to 150. And we are going to show 6 different plots. In those 6 different plots, we are going to show how that reflux ratio is changing our separation of this, right? So, the first thing that we want to do is we want to define a ramp factory. And we have y1, y2, x1, x2. So y1 is going to be your reflux ratio currently, y2 is going to be the end point of that reflux ratio, which is 4, and then 1 is the time step we're going to start ramping up, and then x2 is the time step we're going to start to end the ramping up, right? So now we got to define our ramp itself. And this is a ramp, and this is a time. So in this, what we want to do is we want to do an if statement. So if, let's say if t is less than x1, we want it to return y1. And then down, else if t is greater than x2, we want to return y2. And then we want to do an else statement. So pretty much what this is going to do is, so if the time is before 20 seconds, we're going to keep that same ratio as the reflux ratio as 2. And if we're over the 150 seconds, it's going to be brought back to the 4, right? So what this is doing is keeping these in the middle, and the only thing that's going to be changing is in between those 2 time steps, right? So else, what we're going to return is, now we're going to return our function. So our function is going to be, we're starting at y1, right? And then we're going to be adding, and we want to be adding kind of our slope, as you will. So our slope of y2 minus y1 divided by x2 minus x1. And then we're going to be multiplying this by x minus t minus x1. So as that changes. And so from this, we want to return our ramp. So that's good. Now we are going to say our ramp function is going to be equal to ramp factory. Okay. And what we had inside that was, we said our reflux ratio, we had 4, then we had 20, and then 150. So we're changing from R to 4, which is 2, then we're changing from 20 to 150. Okay, so after this, we know that, now we want to just check to see if this is correct. So what we can do is a t-plot. T-plot is equal to line space of 0 to 500, 300. And so we're going to make an RS function. This is just going to equal kind of an array, a blank array. We're going to update that. So let's do for t in t plot. What we're going to do now is sf append. So now we're going to append that, and we're going to put inside of it to the time is our ramp function. Okay. And then let's do the equals make underscore subplots. And then now we want to do is fig.add underscore scatter. I mean, this doesn't have to be as complex as our other ones, because this is just a check. And y is equal to rs. Okay. Fig.add. There you go. So we have from 20 right here, starting at 2, then it's going to 4, ending at 150. That's great. That's exactly what we want. So after this, now we need to start kind of making this into our McCabe-Tail products. So what the first thing that we did to begin with is we're going to take this up here. So this is our right-hand side that we already created. So we are going to make this again down here, and we're going to change this value to ramp. Okay, so we see here we have R's. Now we have a R ramp. This is for a stagnant R, so we have to change that. So what we can do is we can say R is equal to R underscore ramp, and then this is going to be due to time. Okay, and then before we have to do anything else, we need to go back up here. So when we scroll back up, we see that this here has an R in there, and that means that our vapor is going to be constricted to our reflex ratio at this current moment. So if we don't change that, it will cause problems. So the DS set point is going to stay the same, so just keep that. So just the vapor stuff, bring this down here, and if we put this under this, it should work. So tab over. Okay, so now that R is going to be the RR ramped. Okay, so okay. Now let's do our res is equal to sp.integrate, and then sp.integrate.solve underscore IVP. And now we're going to do our right hand side. I changed that to ramp underscore ramp. Now this is going from 0 to t end. Now what we want to do instead of our guessing function, we are going to guess is up here. So we're going to take this and put it down here. So after that, we're going to do is we do our method is redo, and then our since output is true. Okay. Let's see what res equals. Let's see if we converge. We did converge. Okay. That's fine. Now, with this one here, you might have a problem with before you do your graphs, go over it again and go and click them all. We'll do that at the end. but you might see some error with this number if you don't click through everything again, because I was having problems with that when I did this originally. So that's something to look out for. Now we have our res. So what do we want to do after our res? Well, we are going to change these. So like we did when we split up the McCabe teal, we're going to split up these new things we just did. So we're going to do np.split, and it's going to look very similar to what we already did. Dot split. So when we split it up here, we did that. So let's just do that again. np.split -1, 2. Okay. So then after this, what we wanted to do was we have an x, now we need a y. So this is not correct, not yet. So let's do time solution, because we need to do np.linespace, right? We need to go from 0 to tn. And from that, what we want to do is we want to split it up into 6, right? Because we've already had that. Now with the t solve, now we can split it up. So now we can go underscore x underscore m is equal to np.split of res dot solution and t underscore solve. And we want to split that up to 2, and then we want to have axis is equal to 0. So we don't have a problem with that. So after that, so we have this, now we need to make a for loop. So for I in range, okay, in our range. So currently we have our x, right? So we just made that here. So this is going to give us a plot. And we have our y, and our y plot is going to give us the right range that we need, right? So to do that, we do x shape, and then we do 1. Nope, that's not this, okay? So this is going to go on the second. So you have 0, second, and that's going to be our shape. So our shape 1 is going to be your y, pretty much. So from that, we can do is we want to make a McCabe teal. We want to do XF. And that, so this is similarly what we did. So XS is going to be related to that. XF, we want it to equal our underscore here, and we want to go from comma I. So this will store the time step of this in here. So it will take the I position of time it's in from that one and put it here. So now we have YS. So from YS, again, we know how to calculate YS. So that's going to be alpha times XS divided by 1 minus 1 minus xfs plus alpha times xs. And then from that, take that out, from that, what we want to do is we are going to go up to here for the McCabe-Thiele, and we're going to take the McCabe-Thiele right here. So now, since this is an xf and ys, this will fit right in here. Tape. Okay, so now this fits in there. So after this, that's good. Now we want to go back up to, we have here. So let's take this and let's bring it down here. Now we want to take this and bring it into our for loop. Tap these over. So then we delete these up top. So when we're done with this here, what we need to do is I'm going to put this below. So we have our equilibrium plot for it. But now, so let's say we run this, because this will run, and that's fine. But when we run this, it's going to put all of our McCabe-Thiele into 1, and we don't want that. So what we're going to have to do is we're going to change our rows to 1 and then our columns, and since this is in the shape of the x in the y position, so we just do that. X dot shape 1. Okay, and then from that we have here, we have column is equal to 1. Oh, sorry, that's row. And then from this, we have our column is going to equal, we can do a counter in there. So like this. So let's Control C, Control V, Control V. Okay, so now we have our counters in here. These are going to change crazy colors. So let's do line underscore color is equal to blue. Line underscore color is equal to gray. Okay, and then we have to say figure show. Not show. Okay, so when I said you have to hit the enter, again, after the res, you get something like this. So let's go up here and let's click them all. Okay, so now here are our final graphs. So visually, we can see that it is kind of having a pinch point here. And our steps are very close together. Our steps are getting a little farther apart, more, and more. The less steps you have and the more far apart they are, you have a better separation. And so let's look over here. So this is saying our separation is at 9.19. And then at the end here, it's at, let's just get closer, 9.3 or 4. So that means we're having a better separation. So that means a higher reflex ratio, higher separation in our columns. And you're less likely to have a pinch point as well. And you have more clear steps. So that is the end of homework 3. Thank you.